Optimization of a Structure Using Finite Elements by Tyler Fences and Stephen Utz. Motivation for the topic. We wanted to create an optimal structure to lift something using two pulleys in a tight space where you might be required to mount the pulleys in non-ideal locations. The result is the picture on the right. We started with the Top-Op Optimization 3D program by Top-Op Group. Next, we will get to see a look at the Top-Op optimization in action. In the optimization, the volume percentage was set to 8%, the two back walls were fixed, and a point load was applied in the middle. Next, we use that insight from the Top-Op optimization in NX to get our CAD models that could be imported into Ansys. Both pictures are showing the optimized structure. The one that it is currently drawing is a side view, and this is the isometric front view. The optimized structure had a volume of approximately 17 cubic inches. Next is the unoptimized CAD model. This model features two round tubes that are mounted on the back faces. The one that it is currently drawing is the side view. The second view that it is drawing is the isometric. This design was chosen due to the cantilever structure as the unoptimized structure due to the lack of support. The volume was 21 cubic inches. Now for the FEA analysis of the optimized and unoptimized structure in Ansys APDL. The picture on the left is the mesh of the optimized, and the picture on the right is the mesh of the unoptimized. 10-node tetrahedral elements were used for both meshes. Boundary conditions were applied to the Ansys model to mimic the boundary conditions that were given in the Top-Op optimization. Those boundary conditions can be seen below in the picture. A load of 700 pounds in the negative Z direction, 236 pounds in the negative Y direction, and 118 pounds in the positive X direction were applied. To get an initial understanding of the performance of each structure, a contour plot was analyzed and shown in the picture below. The optimized structure had a deflection of about 3 thousandths, whereas the unoptimized structure had a deflection of about 7 thousandths. This showed clearly that the optimized structure had less deformation and thus was stiffer. Next, we looked at an animation of the von Mises stress. We anticipated that the unoptimized structure would have a higher von Mises stress than the optimized structure. This is the contour animation showing the contour lines of the von Mises stress under the given load. The von Mises contour plot shows areas of high von Mises stress based on the contour graph below. In addition, this picture shows the area of highest concentration of stress of 10,000 psi. The next contour plot animation shows the von Mises stress of the optimized structure. You will notice that the areas of high stress in the optimized structure are much different than the areas of high stress in the unoptimized structure. Additionally, the maximum stress in the optimized structure is significantly less than that of the unoptimized structure. Top-Op reduced the stress from 10,000 psi to 7,400 psi. The stress and deflections were smaller in the optimized structure, even though the optimized structure had a slightly smaller volume than the unoptimized structure.